Hi and welcome to PhD at Living. On my very first chemistry exam in my very first general chemistry class in college, my professor put a really excellent question on there about the pH of the blood. Thanks, Dr. Jones. Essentially, the pH of the blood has to stay between 7.35 and 7.45. Any higher or lower and bad things start happening. So that really sounds like kind of a narrow range. How does the body take care of all that? Well, through chemistry, of course. Let's go. First, let's give a quick rundown of what pH is. pH is defined as the negative logarithm of the hydronium ion concentration in solution. Let's unpack that. Log is the base 10 logarithm. Concentration is in molarity, that is, moles of the hydronium ion per liters of solution, and the hydronium H3O+, drawn very poorly, is the very strong acid that results when you protonate a water molecule. The pH scale goes from 0 to 14, with 0 being very highly acidic and 14 being very highly basic. Yes, I'm well aware the pH scale can go below 0 and above 14, but those are the commonly agreed upon brackets for it, so sue me. Incidentally, we also use H+ to mean basically the same thing as hydronium. While yes, an H+ ion floating around solution isn't going to stay there very long and will almost certainly react with the water, giving you hydronium, it's basically splitting hairs and we use them interchangeably. Another thing we use interchangeably is H+ to mean a proton. The reason is because the hydrogen atom is just one proton, no neutron in the nucleus, and one electron. So you take away the electron and you make a hydrogen ion, we have basically a proton. The reason we use H+ instead of writing out proton or something is to separate it from particle physics. Okie dokie, so now we have pH. It's a way for chemists to talk about the interplay between acids and bases. Which brings up the question, what is an acid and a base? Well, acids and bases have a number of different definitions, but I'm going to adhere to the Bronsted-Lowry definition. This means that an acid is a proton donor. It's something that can give a proton from its molecule. Things like HCl, hydrochloric acid, H2SO4, sulfuric acid, or HNO3, nitric acid. On the flip side, a base, instead of being a proton donor, is a proton acceptor. These are things like the hydroxides of sodium, potassium, and calcium, or things that have amine functionality, such as ammonia. Which brings us to another discussion point. What's the difference between strong acids and weak acids and strong bases and weak bases? Well, it deals with how much of that proton is going to go into a given solution. So for a strong acid, HA, every single proton in that acid, when it reacts, is going to dissociate with the other piece of that acid. The A- here is what we call the conjugate base. So again, strong acid, every single proton, when I react, that is going to come off and contribute to the pH. In a weak acid, and again, remember all this holds with bases except just with OHs instead of H+, instead of every single proton getting released, there's an equilibrium here. So some of the protons are released, yielding that conjugate base and that proton that's going to change the pH, but some of that weak acid is still going to exist in its parent form, which, because the proton is still here, doesn't affect the pH. It doesn't disassociate, it stays where it is, so we have less of a pH effect when we add a weak acid compared to a strong acid that's going to just drive everything way over to the right. Again, all this holds with bases, just switch out H's to OH's. With these definitions, we can see what happens when we titrate or react a strong base with a strong acid. This plot I have here has on the x-axis amount of H+ or hydronium or acid added, and on the y-axis the pH. We start in an idealized scenario with a base called BOH and an acid called HA. We have base at 14 and we add a little bit of acid, and we get not much change in the pH. As we continue adding acid, when we get near the point where the acid amount added is equal to the amount of base we started with, it's called the equivalence point. When that happens, all the base is neutralized by the acid and our pH drops rapidly down to 7, neutral. If we back that out from the pH calculation from the negative log, we have an H+ or hydronium or acid concentration of 1 × 10 to the -7. Not that much. As we continue adding a little more acid, the pH rapidly drops down to 0. If we have the reverse of this, if we have the strong acid at the beginning and we titrate with the base, we have pretty much the same thing, except in reverse. The key here is that when we are near the equivalence point, again, when the amount of acid equals the amount of base, whether we're titrating one with the other or vice versa, we have an extremely large drop or increase, change in the pH with a very small amount of acid or base added. Which brings us to the question of the day. If we know the pH fluctuates wildly around the equivalence point, and we know the body has to regulate the pH of the blood between 7.3 and 7.4, how do we ever make sure that pH is going to stay within that really narrow range? The answer? Buffers. A buffer regulates the pH of a system by reacting a strong acid with a weak base or a strong base with a weak acid. While the pH still definitely changes, the magnitude of that change is greatly reduced by the nature of the buffer. Let's look at an example. If we react the strong acid, hydrochloric acid, with the very weak base, water, we get full dissociation of that strong acid. Remember, hydrochloric acid, full dissociation, every proton comes out, and we're left with that hydronium ion, very strong acid, and the chloride minus conjugate base. The conjugate base of a strong acid is always going to be very weak. If instead of having just the water in there, we have a weak conjugate base, something like the acetate anion, C2H3O2-, when we react with that very strong hydrochloric acid, we then get the acetic acid conjugate acid out of that. We still get that chloride minus conjugate base, which has no effect on the pH, but the key here to the buffer is that when we use a very weak base, we get a very strong acid, very large pH adjustment. With a weak base, strong acid, the conjugate acid is a weak acid instead of a very strong acid, meaning the pH change on here is going to be significantly mitigated compared to that weak base situation. Make sense? Ooh, sorry, I didn't see you there. Is he done yet? Great! Let's talk about how all that boring stuff relates to the blood buffer in the body. There are two big principles at work here to regulate the pH in the blood. The first is the carbonic acid bicarbonate buffer inside the blood. It involves this situation, carbonic acid, bicarbonate, and the H+ proton. If the pH of the blood is too basic, so basic, we can liberate a proton from the carbonic acid, leaving this anion bicarbonate ion. The acidic proton will react with something in the blood and bring that pH down. On the flip side, keeping in mind that this double arrow indicates an equilibrium, and we have some of each of these three constituents in the system at all times, if the pH of the blood is too low, we can react that acidic proton with the bicarbonate anion, come right back to the carbonic acid, and the pH becomes more basic. So basic. If that carbonic acid bicarbonate buffer system isn't enough, we move to the second line of defense involving respiratory compensation. Restated, the body uses breathing to change its own pH. Instead of using that bicarbonate system, we have carbonic acid again, but we decompose into carbon dioxide and water. Remembering our basic biology, humans breathe carbon dioxide out anyway, so this second line of defense uses something we're going to do anyway in order to change the pH of the system. Isn't that crazy? And here's the full picture. We can take these two equilibria, put them together, and see the carbonic acid bicarbonate buffer system and the carbonic acid CO2 buffer system. If the pH in our blood is far too acidic, we react those protons with the bicarbonate to create carbonic acid, and if we need to get even more basic, so completely basic, I'm sorry, I'm done, I promise, we react it out, decompose into the CO2 and water. On the flip side, if we're way too basic and need to get more acidic than we have carbonic acid in the system, we can take CO2 as a byproduct of cellular respiration, react it with the water, get the carbonic acid, and then react into the bicarbonate and the H+ proton that makes the pH, you guessed it, way more acidic. And these are two big chemical processes that the body uses to stay alive and do biology and stuff. And that sounds a whole lot like biology, and you know we don't deal with that around here. So I'm just gonna go. See you next time. I never drink wine.